In today's video, I want to talk about Hytale's threading model from single thread to multi-world architecture. What you will learn today, you will learn what is multi-threading. We talk about threads, we talk about race conditions, we talk about the old world, like how single-threaded servers work and what are their limits, like for example, Minecraft, which uses a single-thread system. We will look about Hytale's solution to multi-world threading architecture and what that means for your modding and your mod development. What are the new rules? What save, what crashes, and why? We will talk about how you can predict your data to develop thread-safe types for plugin state, for example. And we will talk about patterns for modders, like real code examples from Hytale itself. And I will show you at the end of the video a little example of a global kill counter plugin that tracks kills across all worlds. So this is a very important topic because Hytale itself runs on a multi-threaded architecture, and that has very many different implications on how you need to develop your mods and plugins. So before we dive in, please make sure to join the community. I just started a Discord server for Hytale developers, and if you want to help build and moderate the community, reach out. Here's my website, here's the Discord link, and if you want, follow me on Twitter. So let's begin with understanding what multi-threading even is. So what is a thread? So I keep hearing about threads and multi-threading, but what does that actually mean? So imagine a kitchen. A thread is like a chef following a recipe step by step. In a single-threaded kitchen, one chef does everything: chopping, stirring, checking the oven, one thing at a time. And you may say, that sounds slow, and yeah, it is. Now imagine 5 chefs working together. One chops, one stirs, one checks the oven, all at the same time. Now that's parallelism. But what if 2 chefs need the same knife? They have to coordinate, and that's the core challenge of multi-threading, coordination. More on that later. So in a single-threaded architecture, everything happens one after another, where within a multi-threaded architecture, all happens at the same time. So the trade-off is that multi-threading is faster, but it also requires careful coordination when threads share data. So what exactly goes wrong when 2 threads share data? So let's say we have a counter starting at 0. 2 threads both want to increment it. You'd expect the result to be 2, right? And you would say, of course, because it starts at 0, it adds 1 equals 2. But like the expression counter plus plus in Java, it isn't just one operation. It's actually 3 because it reads the value, it adds 1 and then writes it back. And another thread can interrupt between any of those steps. So if both threads read 0 before either writes, they both compute 1 and write 1. And the result is 1 instead of 2. That's called a race condition. So, for example, we have the counter plus plus expression, which compiles to 3 bytecode instructions in Java. So both want to increment this variable. First, in bytecode, it's called getField. In thread A, it's 0. Thread B does exactly the same. So both read 0 because, as we know, thread A and B, they coexist and they can execute things simultaneously. So the next step in counter plus plus is to add 1, and we do this of the value we have read, and that is 0. So both threads define, okay, hey, the new value is 1. Then thread A puts the field to 1, and thread B does the same. So we wanted to increment the variable 2 times, but at the end our counter is at 1, but we expected 2. So this is a race condition. And race conditions are unpredictable. Your code might work 99% of the time, and then randomly fails when timing is sort of unlucky. So when it comes to multi-threading, we have a couple of key concepts. A thread is a sequence of instructions that can run independently. Concurrency means that multiple tasks making progress, not necessarily simultaneously, but like multiple tasks. Parallelism means that multiple tasks running at the exact same instance, and that needs multiple CPU cores in order for it to work. A race condition is a bug where output depends on unpredictable timing of threads, and thread safe means code that works correctly even when called from multiple threads. The goal is to get the speed of parallelism with multithreading while avoiding race conditions. So let's look at how the old world worked, like single-threaded game servers. Think Minecraft, for example. So how does a game server actually work? Well, every game server runs in a loop. Over and over, it does three things: process input, update the game state, and send results to players. And each complete cycle is called a tick. And that's like a heartbeat, right? And yeah, exactly. The speed of that heartbeat is TPS, ticks per second. Minecraft, for example, runs at 20 TPS. Hytale defaults to 30 TPS. If your server, for example, runs at 20 TPS, it processes 20 ticks every second. So a second consists of 1000 milliseconds. We divide that by 20 ticks per seconds, and we get 50 milliseconds per tick. And for example, the time between a tick is 50 milliseconds in Minecraft. In Hytale, it would be 33, and in fast-paced games, for example, it would be 60 milliseconds. So the server must finish all work within this time. If a tick takes longer, the server falls behind. So in a single-threaded server, one thread does everything. And let's say we have 3 worlds in a single-threaded server, world A, B, and C. If world A takes 30 milliseconds to process, world B and C must wait because everything is sequential. And if world A takes 60 milliseconds and our tick only gets us 50 milliseconds, the server can't keep up and everyone lags. So we need to write performant code in order to execute all the updates we need to do within our time frame of 50 milliseconds, depending on how many ticks we want to run per second. So what does lag actually... I jumped too far. So what does lag actually feel like for players? Well, when ticks take too long, the server falls behind. You can experience several symptoms. For example, something called rubber banding. You walk forward and then suddenly snap back to where you were. The server rejected your movement because it was still processing old data. Or you have delayed actions. You click to attack and nothing happens for a moment, and then suddenly the hit registers. In single-threaded servers, if any world is slow, everyone feels it. And that's the fundamental problem we need to solve. So let's make this concrete with a real plugin idea, a global kill counter. It tracks kills across all worlds and shows a server-wide leaderboard. Well, and you might say, hey, that sounds straightforward, so just count the kills. And in a single-threaded server like Minecraft, yes, all kills happen on one thread. Easy. But in Hytale, each world has its own thread. Multiple worlds can trigger, like the dev system, simultaneously, and that changes everything. And we will look at that global kill counter as an example throughout this tutorial. So let's look at Hytale's solution for multi-world threading architecture. So as we said, Hytale doesn't use a single thread, right? Exactly. Hytale gives each world its own thread. World A, for example, runs on thread A, world B runs on thread B. So if world A lags, then world B doesn't notice. They run in parallel, completely independent. You see, single threading, everything is sequential, one world at a time. If A lags, B and C wait. But in Hytale, everything runs in parallel, all worlds at once. So if A lags, B and C simply don't care. Let's look at the hierarchy of Hytale's multi-threading architecture. At the top, we have the Hytale server. It's the root of everything. It's a singleton, which means only one exists, and it owns a so-called scheduled executor for background tasks. Then we have the universe, which I also explained in my tutorial about the entity component system. It's a container for all worlds. It is also a singleton, which means only one exists. It has a method to thread save player lookups with a concurrent hash map, but it has no own dedicated thread. And then we have worlds. Each world has its own dedicated thread. So we have an entity store, which is thread bound. We have a chunk store, and that's also very important. Worlds can have different ticks per second per world. So what is a scheduled executor. And what is a thread pool? So remember our kitchen analogy? A thread pool is like having 5 chefs on standby. When a new dish order comes in, an available chef picks it up. You don't need to hire a new chef for every order. And scheduled means you can say, do this in 5 seconds or do this every minute. The executor managed timing for you. Hytale uses that for background tasks like autosave, for example, or cleanup or delayed actions, code that shouldn't block the game. So we have something called thread bounding. So what's thread bound? For example, the entity store in each world can only be accessed from that world's thread. So why does Hytale enforce this? On the one side, to prevent race conditions. On the other hand, to make bugs obvious. Because if you try to access a entity store from the wrong thread, your server crashes. So it means, hey, you have to take care of that. It doesn't cause for silent corruption. And you have a clear ownership model, which should make things easier. You have different worlds and have different threads. And each entity store of this world is bound to its thread. So what does thread bound mean exactly? As I just explained, each world entity store can only be accessed from that world's thread. Try to access it from another thread and Hytale throws an exception immediately. So why crash instead of just logging a warning, you might ask? Because silent failures are worse. Race conditions corrupt data randomly. A crash tells you immediately, hey, fix this now. So the crash is sort of your friend. So every store records which thread created it. This is from the store implementation in Hytale itself. So at creation, it captures the thread and then it has a method which asserts the thread and throws an illegal state exception if the assertion was not made in the right thread. So it is called on every operation, get component, add component, remove component, take everything that has to do with entities and so on. But the phantom benefits are like no race conditions, bugs found immediately, and clear error messages. So that really is the power of isolation. We have independent performance, because if world A lags, then world B doesn't care. We can define different ticks per second per world. Let's say our lobby only needs 30 TPS, but a minigame should run at 60 TPS. We have true parallelism because we can leverage multiple CPU cores and multiple words processing simultaneously. We get to define clear boundaries. You always know which thread you're on, and it scales with hardware. More cores means more parallel worlds. And this means that Hytale can scale to massive player counts by running worlds in parallel. So let's take a look at the new rules, sort of to say, like writing thread-safe plugin code. So how do I know what's safe to call? And that's a very great question. There are exactly 2 categories: things that are always safe and things that need the world thread. So let's look at some examples one by one. Always safe, for example, is universe.get.getPlayer. It uses a concurrent hash map internally. It is thread safe by design. Network operations are also thread safe because packets queue up properly. Getting data from the player ref is also safe because it's immutable. Once set, it can't change, so no race conditions. And the scheduled executor of the Hytale server itself is a threading tool, so scheduling is always safe. So why is it safe? Because these operations either don't touch world data or use thread-safe data structures internally. So world thread only, or differently said, will crash otherwise. For example, store.getComponent, because this method reads entity data. It must be on the world thread. The same goes for store.addComponent, because it modifies an entity. It must be synchronized. We have also remove component, which changes entity structure, and that's definitely not thread safe. And just to sum it up, almost every ECS operations, from systems to queries to command buffers, everything in the entity store, so those will crash if we are not in the same thread. These touch the store, which is thread bound. Assert thread will throw an illegal state exception. So we have methods that we can access from any thread, and we have methods that we can only access from the world thread only. So we need something in between. We need like a bridge. And every world has a method called execute. And this world.execute method is the bridge between two zones. Almost said something with profanity in there. Holy moly. Okay, using world.execute. So how do I get from any thread to a world thread? That's exactly what world.execute does. You give it code and it runs on the world's next tick. So let's look at an example. We have, for example, the Hytale scheduled executor. And inside this lambda expression, which is just like a way to define a method inline, we can say world.execute and give it another lambda expression and say, hey, run this store.getComponent method on the world thread it's safe. And inside the scheduler, we say, hey, please run this every 5 seconds. So execute queries your code to run safely on the next tick. So the common mistake would be to, for example, call the scheduler and just call store.getComponent. It would be called on the wrong thread and would throw an illegal state exception. The scheduled code runs on the executor thread, not on the world thread in this example. We need to wrap it inside a world.execute method to get the store.getComponent on the right thread, on the world thread, and world.execute does exactly that. So a quick reference, if we want to send a message, if we want to get player by UUIDs, if we want to schedule a task, it should be always safe. But if you want to read components, add components, or heal the player, for example, what we need to do is within a specific world thread. If you're not sure if you're on the world thread, for example, abstract player command takes care of that for you, wrap it in world.execute. So what if I'm not sure which thread I'm on? You can check. You can access the current thread and it tells you on which thread you are. World threads are named, for example, World Adventure, World Hub, etc. And what if I get an illegal state exception? Well, that's the system helping you. You need to wrap your code in world.execute and try again. The crash is sort of your friend. It tells you exactly what to fix. So, okay, we now know about multithreading and how Hytale works, but what does that mean for my mod development? What do I need to know about thread safe states? And why do I need this? Well, if world.execute handles thread safety, why do I need more? And that's a good question. Hytale only protects the entity component system. But what about your plugin data? And like what, for example? Remember our global kill counter. Multiple worlds incremented simultaneously. That's your shared state, and it needs protection. If this, for example, is our kill counter, and we define a variable global kills and have a method on entity killed and just increment our variable, our counter, we get a race condition. Because global kills ++ is secretly 3 operations, read, increment, and write. 2 worlds can read the same value, both increment, both write, and 1 kill is lost. So let's go quickly through a concurrency refresher. So what exactly does make a code thread safe? So thread safe means code works correctly even when multiple threads use it at the same time. No corruption and no lost updates. And global kills isn't thread safe because it can be interrupted. Thread A reads 5, thread B reads 5, both write 6. You lost a kill. This is a race condition. So Java's solution for that is atomic types. We can say, hey, atomic can't be interrupted. And atomic integer, for example, makes the whole read, increment, write happen as one indivisible operation. No thread can interrupt it. And you also have classes like atomic boolean, atomic long, or atomic reference for objects. So if we look at a real example from Hytale inside the teleport plugin, we have a variable called loaded, which is a atomic boolean. And inside this teleport plugin, on the initialization, we can say, hey, compare and set, only one thread can pass this check, and we can guarantee to run the method initialize warps exactly once. Compare and set checks and sets in one atomic operation. It's perfect for one-time initialization that might be triggered from multiple worlds. And what about maps? Like, what if I want to track kills per player across all worlds? You would use a map, but hash map, for example, is not thread safe. Multiple worlds, modifying it can corrupt the internal structure. So you might ask, okay, what else should I use? And the answer lies in the concurrent hash map. It's designed for multi-threaded access, and Hytale uses it for the player registry in the universe, for example. So instead of using a hash map, we would use a concurrent hash map. And you can see nothing really changes right now because we can still use the map interface for itself, but we also have like atomic increment patterns to better initialize and update our data structures. So merge, for example, is an atomic operation. There is no race condition possible, but you also see that multi-threaded programming is like a bit more complex than just single-threaded programming. So that's a whole new paradigm itself one should look into, and I will do another video about it where we just tackle Java concurrency. Another great feature is the keyword volatile. So what if I just need a simple on-off flag, for example? For flags that one thread writes and others read, use volatile. It ensures all threads see the latest value. So we can say private volatile boolean tracking enabled true false, and all worlds can see when tracking is disabled. So it sort of propagates this value to every thread so that no caching can result in like a stale value or something like that. So here's a quick reference. If you need a counter, use atomic integer. If you need a one-time init, use atomic boolean. If you need a shared map, for example, use concurrent hash map. And if you need a simple flag, use volatile. The rule of thumb is, if multiple world threads touch your plugin data, use thread safe types. So this would be our complete kill counter with a atomic integer, with a concurrent hash map, with a volatile tracking enable flag, and then we have this method one entity killed, where we can increment and get and merge. And in the next slides, we will show how to do that with the Hytale API. But before that, the mental model sort of shifts. So does my plugin have data shared between worlds? If no, regular Java is fine. If yes, you need to use thread safe types: atomic integer, concurrent hash map, or volatile. So that's like, oh no, there is something German. I wanted to delete that. But yeah, if you need world data, use world.execute. So let's look at some real examples from Hytale. So our kill counter with the real Hytale API would look like this. We have a kill tracker system, which extends devsystem.onDevSystem. We define inside the kill tracker system an atomic integer and a new concurrent hash map, and we override the onComponent added method. You see, entity components, if something happens, a component is either added or removed. And we can listen to that onComponent added event and look for the dev component, and if it exists, okay, then we know the player got killed. And then we can check, okay, by which source, for example, the player got killed. Did he get killed by a mob, a player, or by the console? And then we can, for example, call increment and get and do a operation on our concurrent hash map. So this would be a complete thread safe example. Multiple words can trigger onComponent added simultaneously, but atomic integer handles it. So the most important pattern is will.execute. It bridges threads. For example, in the teleport plugin, it is exactly like that, where we wrap a method call inside the world.execute, where we need to get the world beforehand, and then, for example, create a new warp. Or cross-world communication, that we, for example, need to notify all other worlds about a removed world. So we get the universe, and we get the worlds, and iterate through each world. And for each iteration, we call world.execute. So the second pattern would be scheduled tasks, where we want to run something every X seconds, for example. So the objective plugin has a autosave feature for objectives for every 5 minutes. So we define Hytale server, scheduled executor, and then schedule fixed delay. And then we call like this objective data store and this method save to disk all objectives. And then we say, hey, please run this every 5 minutes. For our kill counter, we could do like a periodic leaderboard broadcast where we get the global kills and then we send a message with like total kills equals the total amount we have saved. So code in scheduled executor runs on a separate thread. Don't forget that. If you need to touch the entity component system, wrap it in will.execute. So how do I save kill stats to a database without blocking the game? So we would use something called completable future to run database operations in the background. So this is like asynchronous programming. We call completable future, define the method run async, and inside this lambda we define, we can say, hey, database.savekills, and this runs on a background thread. The key is to offload heavy input-output operations on a background thread so the world thread itself stays responsive. Another pattern would be cross-world teleport. So how do I send a player from one world to another? And the key is capture the data first and then queue it on the target. So we capture the data first, we're on source world thread, like we get the target position, the target rotation, and then we execute the teleport on the player's world. This is like from the teleport to player command from Hytale itself. So critical, don't read from the other world inside execute. Clone the data first while you still can, because this will lead us to another issue we will go through just in a bit. We can also do universe-wide broadcasts, for example. So, universe.get is always safe. We can send a message, for example, the server shutting down in 5 minutes. Internally, it iterates through concurrent hash map of player refs, and for each player ref, it sends a send message. So we can also find players by UUID or by name, for example. So universe operations are designed to be thread safe. You can safely send messages, look up players from any thread. So one common mistake is to store from wrong thread. So now, for example, in a scheduled executor, please wrap it inside world execute because the scheduled executor runs on its own thread. It also is a very, very dangerous mistake to block the world thread because, for example, if we have like this completable future and we call join, which executes this completable future, it blocks the world thread where we should really embrace asynchronous programming and then queue it into the world execution queue to like get things going. So we should never call join or get from the completable future interface on a world thread because it blocks the entire tick. Mistake 3 is shared mutable state, as we just had in our kill counter example. If we have like shared mutable state, we should use atomic integers or atomic booleans. Each world runs on its own thread. If your plugin has global state, multiple threads will access it. And the next thing is a deadlock. So what is a deadlock? When two threads are each waiting for the other to release something, neither can proceed. So they're stuck forever. And that is a so-called deadlock. So how would you avoid that? You simply don't block inside world.execute, and that's easier said than done. Don't block inside world execute waiting for another world. Use callbacks or asynchronous patterns instead. So this would be a deadlock. We execute something on world A, and we are now on world A's thread, and there we call world B.execute and wait, and then we wait for world B. But what if world B is currently waiting for world A? So that would mean a deadlock and your server would need to be restarted or it crashes even. So the more safe method would be to use callbacks, don't block. Inside the world A thread, we prepare the data on world A and then we queue the work on world B, which is non-blocking. So it runs when world B is ready. Never wait synchronously for another world. Always use execute, which is non-blocking. And I know it might sound very confusing at first, and it is. It really is. Asynchronous programming and multithreading and concurrency is not easy. So don't be like taken down from this if it doesn't make that much sense to you right now, because all of those examples, all of those paradigms, all of those patterns are some things that you need to practice a lot to get that mental shift inside your brain to look at things a different way than with just a single-threaded programming paradigm. So if we summarize this, if you want to run code on a world thread, use world execute. We have the scheduled executor. We should use completable futures for heavy asynchronous worlds. We can do cross-world teleports, for example, when we first capture the data and then use world execute. We have the universe for broadcast, for example. We can do shared counters with atomic integers and shared maps with concurrent hash map. So let's summarize everything we did and the key takeaways. So what did we build? We have our global kill counter that taught us everything. We have the problem, which means multiple worlds, multiple threads hitting our counter. We have explained the architecture. Each world has its own thread, and ECS, Entity Component System, is thread bound. The bridge is world execute, which gets us onto the right thread. And we have the protection for our plugin state or mod state with atomic classes and concurrent hashmap, for example. And the patterns are scheduled tasks, async operations, and cross-world communications. So there are basically 3 rules. If you need ECS access, use a world thread. If you have shared plugin data, use thread-safe types. And never block waiting for another world. Use asynchronous methods. Here is a little cheat sheet for everything we just covered. Make a screenshot if you want. And here is a little overview for concurrency quick picks. I will make another video about Java concurrency. And then thanks for watching. Be sure to check out the website, like and subscribe this video and my channel, and please join the Discord so you can take part of this great community. Thank you for watching and see you guys soon. Bye!